3.1, first question is saying, draw a neat labeled circuit diagram to show how the speed of the series direct current motor would be controlled by connecting a diverter across the armature. By the way, that's a resistor there, the diverter resistor that has to be connected. It's a variable resistor, as a matter of fact. Right, so how is it going to be connected? All right, so this is how the diagram looks like. Right, so having a series wound machine, so it means we have our field winding connected in series with, so we have here, there is our diagram, we have the armature, there is the armature, right? So this is the symbol for the armature, right? And then of course, we have the terminals, label them positive and negative. It's a DC machine. Right, so that's our armature there, and we can indicate the current. That's our IA there, current, and of course there is the diverter resistor. It must be connected in parallel with the armature, so we will indicate it here. Right, there is the symbol for a resistor, right, and then the variable resistor we indicate with an arrow to show that it's a variable resistor, that diverter resistor that we have. So this marks our diagram, and of course this is the series field. This is the series field, and this is the armature with its own resistance there. Right, so that's the armature diverter method we have. Okay, let's quickly go to the next question. Explain the function of the no volt relay in the direct current machine. So it simply ensures that, so the no volt relay, it ensures that the starting handle is replaced to the off position when the supply is cut off. Or we can say a no volt relay automatically disconnects the motor from the supply in the event of the supply voltage dropping below the rated voltage. Right. It might interest us to know that indeed this no volt relay, in the event of a power failure, it de-energizes and so ceases to attract the stator arm, which then moves back to the off position. So because it is spring-loaded itself, so the motor cannot start again until the starter is deliberately opened. That's the purpose it actually serves. Right, so that's the explanation, of course, we had given there, the first two explanations we had given, just adding some few things regarding that. Okay, so a 200 volt DC series motor draws 50 amperes from the supply. The armature resistance of the motor is 0.25 and the series field is 0.4 ohm. Calculate the machine's constant if it operates at 890 revs per minute and the useful flux per pole is 29 milliwebers. Right. The motor's constant is found on the equation that is connecting the relationship between the speed and the flux and the EMF. It says E is equals to K N times phi, where K is the motor's constant and it has no units. Right. So how do we go about it? How do we calculate it? Right. Making K the subject, then we can say divide by N times phi, divide by N, multiply by phi, and that will give us K is equals to E over N phi. Okay, so substituting what we have, do we have E? Apparently, we do not have E, but the information is that of a series motor. So how do we calculate the back EMF in a series motor? E is equal to V minus the other two voltages that we have, IA-RA plus IA-R series, taking note that, so IA-R series, the series resistance, taking note that in a series machine, the field winding, since it is in series with the armature, with the armature, just that part alone is the one that I just wanted to demonstrate. Since it is in series, it means the terminal voltage is one potential difference, is the main voltage we have, because the motor, and we have a voltage here, IA-R series, is telling us that IL, the voltage from the supply, is equal to IA is also equal to I series, the current passing through the field winding. So we are simply saying all the currents we are having in a series generator, they are basically equal, right? So for that reason, it's possible then to say of the three voltage drops that we have, there's also RA here, there's a voltage drop, IA, RA, right, at the armature, right? So because of that, it means it's possible then to calculate it in this way. So V minus, we can factor out IA, the common factor, bracket RA plus what? Plus R series. So we can still do that. So substituting the values into that, it means to calculate the EMF 200 minus, right, 50, bracket 0.25 plus 0.4. That's how we calculate the EMF in a series motor, right? So simplifying that, it's going to give us 200 minus 15 times that, it's going to give us 167.5. So we have the EMF. Hence, we can come now into our formula, 167.5 divided by N, that's 890. You take it as it is in rest per minute, multiply by the flux per pole, 29 milli is times 10 to the power of negative 3. So we punch that on the calculator, right? And it's going to give us 6,489773, which to 3 decimal place is going to give us 6.490, just like that. That becomes the constant, the motor's constant. Okay.